Here in Chapter 7, we're going to be talking about some really interesting stuff regarding mental imagery, cognitive maps, and such. There is a lot of information here about some research that we'll talk about, and that's why there are so many slides in here. Not every slide takes a lot of time to go through, but there are some certain notes in here that'll help guide you through interpreting the research. And of course, also, please refer to the text for more details. But I certainly want to prepare you as much as I can for understanding some of the nuances in the research in case you have questions. So let's jump right into it. By way of introduction, we're going to be looking at the way that perception, and we've already learned about this, requires both bottom-up and top-down processing, and that those processes that give rise to your ability to create mental images usually come from those top-down processes. So what you know about experiencing information, we'll talk about things like propositional codes versus analog codes that kind of identify that. And mental imagery is a knowledge-driven thing, which is why you kind of have to have top-down processing, because top-down processing relies on knowledge and experience, and it relies on things that are stored in the long-term memory, including things like visual cues and things like that, which are stored in the top-down processing. Stored. They're required by the top-down process, and also are stored in long-term memory. So let's talk about where visual imagery comes from a classical standpoint. So the research on imagery, on visual imagery, comes from several different areas, and they've kind of had different names. So sometimes it's called mental imagery, or just simply imagery. But there's also, an auditory imagery. So we tend to make a distinction between auditory and visual. So just for the sake of mentioning those terms, mental imagery usually is in terms of visual and auditory imagery for the sake of what we're talking about in this chapter, because we are going to also include information about cognitive maps. And that tends to be more visual, but we'll also do auditory imagery. Those are the two that are usually a lot easier to talk about, especially because other types of imagery, like sensory imagery, is a little bit more difficult to study, especially in a classroom setting. So mental imagery is one of those things that STEM has been very interested in. So the science, technology, engineering, math, and arts too. I think STEAM is kind of, to borrow a pun, picking up steam as an initialism for those kinds of fields. Mental imagery is very interesting to those fields because it relies on largely the spatial skills that you need in order to do things like mental rotation. We'll also talk about perception versus imagery. And remember that it's a tricky thing because perception is already the mind's interpretation of a stimulus. And then you have the matter of imagery. But perception requires the stimulus to come in, and then initially you use bottom-up processing in order to identify something, especially if you haven't seen it before, if you're a baby and you're learning what everything in the world is. But imagery is a thought process. It's something that you create a mental image of based on your experience or what you know about the world, which again supports the idea that mental imagery is a top-down process because it only comes from what you already know. Even if you've experienced something, you already know what the image is in order to be able to create it in your brain. Otherwise, you're just perceiving, and that tends to be bottom-up, especially, like I said, for first time learning about something. And historically, by the way, mental imagery has kind of gone back and forth in terms of legitimacy, depending on the type of psychologist that is observing it. So the early behaviorists didn't really like the idea of mental imagery because it wasn't directly observable, whereas other folks, especially in the humanistic kind of second, third wave-ish of psychology, we're starting to think about the internal processes and what's important there. Mental imagery was also something that was important to the early psychologists that were doing things like therapy and psychotherapy, things that happen between your ears, so the intrapsychic forces. So there's kind of been a struggle between the different types of psychology that have developed in the last 100 years or so, 150 years or so, and what mental imagery is and how important it is. Because mental imagery is one of the things that is not directly observable. You can't look at somebody's brain and see what they are imagining. So in that way, it makes it a pretty challenging topic to study, but we can do it. So how do we do it is the real question. What we know about mental imagery is that it represents something in the physical world, something that we sense. So if there is something that we sense in the physical world, we can make judgments about that thing even in its absence. So so for example, if we can imagine what the backside of a house could look like based on looking at different perspectives of it, except for the back, then we can usually make some kind of assessment of it. Or if we had like a map, and we looked at the map and then we put the map away, we could go find the thing in the map because we can access that mental image of the cognitive map. We're kind of blurring lines a little bit because cognitive maps come from mental imagery, and cognitive maps has a special term. But the deal is that we recognize that we can study something that's unconscious or something that's a mental process by observing what happens when we put it into our conscious effort. So one of the ways that we can observe mental imagery, especially visual imagery, is through something called mental rotation. So remember, the major point here is that imagery is not observable and fades quickly. So as you imagine something, it kind of, you see it and then it goes away. You can recall it each time, like you can refer to it in your long-term memory. But each image is fairly volatile. It kind of dissipates quickly. That's why we have long-term memory, so that you can store those things without having conscious awareness of them at all times. We would be very full. Our episodic buffer would be incredibly full. Our visual spatial sketchpad would be incredibly full if we had to have everything in our conscious awareness at all times. A classic example of mental rotation is the demonstration from 7.1. This is a very three-dimensional mental rotation task, and this has been used for lots of different things, including intelligence tests, to determine what kind of spatial skills that somebody might have. And you could try that, and to determine if there is a difference in the shapes in demonstration 7.1. You look at the pairs, so you look at pair number A, look at me go, at pair letter A, and you can determine if those two shapes are the same shape, but they're just rotated, or if they're different shapes. And we're looking at a couple of things. We're looking at speed and accuracy. So we want to know if if the shape rotates to the same shape, so if the two shapes are the same shape, just rotated, and how quickly you can make a correct determination. And in some cases, the shapes are just rotated kind of on a two-dimensional plane. Like if you stuck your hand out and just twisted it, you could rotate it like it was on a wall or something like that. The other one is in B is an example of a three-dimensional rotation where the rotation is not just spinning it around left and right like a dial, but it has to rotate front to back also to determine if there is if they're the same shapes. So it can be very difficult to determine that, to know what the shape looks like compared to the comparison shape. That's a really awkward way of saying it. It can be difficult to know if there is a shape that's similar if it's rotated in a different dimension other than just simply rotating it on a plane, like in a dial or on a clock or something like that. The decision to make the correct choice and how fast you make it is dependent upon how rotated the object is. This is probably not a secret to you. It's not a surprise, but the larger rotations take more time to determine if they're similar. So again, this is the example of the experiment. So you have objects in A. Are these the same? And as you can see, these just rotate around in a circle to determine if they're the same shape. In B, you rotate them front to back, so imagine a third dimension here to determine if those are the same shape. And also that also includes this kind of z-axis to twist around. So this one you need to spin it around this way, but in B you have to rotate it kind of like on an axis to determine a vertical axis to determine if those are the same or not. And the same thing in C, you have to rotate it a certain way that is not just spinning it in order to determine if that object is the same from left to right. And I'll leave it to you to find the right decisions. So one of the outcomes from this study is that can we map to see how difficult it is to rotate an object based on two things. How much it's rotated and in what way it's rotated. So if I look at a picture and it's not rotated at all, and I'm comparing it to another picture to see if it's the same, my reaction time is pretty quick. It's right on the mean, more or less, and there's not a lot of variation in there. You can see the error bars in there. As the angle of rotation changes, the amount of error goes up and down. That means that even though people kind of still tend to fall on this average line here, the reaction time goes up in general, but the error also goes up. So people are likely to make, that's not an accurate thing. The statistical error goes up, meaning that there are more variations in this reaction time as you go up. So what this means is that it takes longer for your brains to rotate an image based on how far away the two images are rotated from one another. And that's one of the most interesting findings that came out of this mental rotation task, is that, it's not just how is it rotated, but how far is it rotated. So this is the picture plane pairs. These are the ones that you just rotate in a circle to determine, like on a two-dimensional circle, to know if it's a similar shape or not. On the depth pairs, those are the pairs that get rotated kind of like front to back, or they spin around, and those are more difficult because they happen in 3 dimensions. And in those cases, we have a lot of variance. Even if they are not off by a whole lot, we have a lot more variance in the length of time that it takes you to come up with that correct solution. But what's also interesting is that once you get up to the 160-degree mark, that's still less than about 4 seconds. But for the 160-degree mark for the picture plane pairs, that's more than 4 seconds. So there is something interesting about that. Even though there's a lot more variation here in the depth pairs, overall, the total sum of time it takes to rotate a 160-degree rotation pair is a lot more. That's probably not. I don't know if it's a lot more. I haven't done the statistics on it, but it's more than 4 seconds. And for the depth pairs, it's only just shy of 4 seconds. So kind of an interesting finding there. Other stimuli, like letters of the alphabet, have yielded similar results in mental rotation. So the more a letter of the alphabet, for example, is rotated, the longer time it takes to make an accurate judgment of whether or not it matches another letter or it's reflected or whatever. Same kind of thing with handedness, but there's some interesting findings about handedness too, in that if a right-handed person sees a picture of a hand and has to rotate it to determine which hand it is, a right or left hand, that a right-handed person has an easier time doing that if it's a right hand than a left hand. However, left-handed people don't have a difference in determining if a left hand is rotated versus a right hand. So they can identify if it's a left or right hand at the same speed. And what that suggests to me is a bias for right-handed people, and that left-handed people have to do more with recognizing right-handedness than right-handed people have to recognize left-handedness. So in that way, people can recognize left-handed people can recognize left and right hand the same, whereas right-handed people have a more difficult time recognizing left hands. Same kind of thing about upside down versus upright pictures, where people have an easier time identifying upright pictures compared to upside down pictures, and they do it faster. More research on this indicates that older people have slower reaction times in general, but especially to mental rotation tasks. But people with American Sign Language fluency are able to rotate mental images faster than people who don't have, or than people who don't use ASL. And that's because American Sign Language is a signed language, which means that you produce it from your vantage point, but also read it from another vantage point, which compared to your vantage point is flipped 180 degrees. So in that way, they are able to simultaneously produce information in from a 0 degree rotation perspective, but they are used to seeing it in a 180 degree perspective when they are looking at it. So in that way, they're able to instantaneously recognize their same signs but flipped. There are two basic factions that have taken sides in the imagery debate. One is there a comparison with imagery like perception, like do we see something and we just have an image of it, or is there some kind of linguistic type analogy to that? And I got to be careful about using the word analogy because that actually fits analog. But is there some kind of language skill that's useful in encoding information in terms of imagery? And what the terms that have been developed for describing this difference is that we can encode images as analogs, or use an analog code, or as a picture, or as a propositional code, meaning that we have descriptors of the images, and those propositional codes are used to define what an image is in terms of its characteristics. So we're going to step through those, each one, in a little bit of detail. The analog perspective is that we have an image of something, and that image, if we close our eyes, we would see the thing. It's as if we've taken that proximal stimulus, it is registered on our retina, and the distal image registers on our retina, and then we have this representation of it that gets stored. That's the basic way that the analog perspective suggests that the image is registered. And that was kind of common among many theorists. And in that way, mental imagery was very related to perception. The way that we perceive something is the way that the image is stored, how we make sense of it. And that we have responses to mental images that can mimic the response to the actual physical object as well. In general, people who oppose the analog perspective, and people who are of the analog perspective as well, they agree that they don't really suggest that there's like this picture that's like etched in your head. You have to like create it. You can't like produce it. You imagine the picture, if that makes sense, as opposed to like seeing it as if you like close your eyes. And if you had a dream, for example, you would see the actual image or something that's happening to where the image is quote unquote seen. But with mental imagery, it's not actually seen. You imagine it being seen. I know it's kind of a funky thing to think about, but there is a difference between the way that something is seen in terms of the perception of something, and how something is seen in terms of the mental interpretation of it. Also, by the way, we tend to lose resolution in the image that we're looking at, and this is evidenced by the fact that we lose details of things that we've seen before. Imagine seeing a sign on the side of the road, that your billboard you've driven by 100 times. You've seen it, you've registered all the information onto your retina, and it's gone into your brain at some level, depending on how well you've processed it, but you can't recall every little bit about it. And that also suggests that if you needed to imagine something, that you would probably miss some details, usually details that aren't important to whatever you would need to recall, but the details are missed in general. On the other hand, we have the propositional perspective. In the propositional perspective, everything that you would see would be stored almost linguistically. Like it would be a description of it, as if you were like captioning the thing that you were trying to see. So if you look at a red ball, you would have like this propositional description that says something like, it is a sphere, it is red, it appears to have 3 dimensions to it, and it's, more or less round, because we know that balls don't have to be exactly round. So you would have this kind of description of it. And this was the initial contribution by Zenon Palishin, and that's his name, Palishin. All those Y's are pronounced as short I's, so Palishin, that'll work fine. And the mental image is not necessary in imagery, where you can be describe something and you can build it, and that's true. If someone said to you, "Oh, if you said, what am I looking for?" and they said, "Well, I'm looking for this yellow curved thing." And it's longer than it is wide, and it has a stem on one end, and it has a sticker on it too. So you could describe that, and you would be able to look at things, and you'd be able to okay, that's not it, that's not it, that's not it, by comparing that proposition. But you could also imagine that it's a banana. Or you could redefine it as a banana based on that, and then you could compare other things to banana to determine if it's a banana. So if you're looking at an apple, you would know that that doesn't fit the propositional code, so you would move on to the next thing to determine if it met the propositional code. And we'll go into later in class about how we organize these things and how we create hierarchy and taxonomy, because lots of times you recall an object based on the most important characteristic. And what is the most important characteristic? Well, it depends on what you're trying to look for. If you're looking for a banana, probably the most important characteristic that you can look for is a yellow banana. But if you're looking for a yellow banana among a bunch of other yellow things, I can't imagine what other yellow things would be. But if you were, then you'd have to think of a different, most important characteristic that's distinguished among bananas, but not the other things. So let's say you're looking at, I don't know what, a grapefruit. Grapefruits kind of look yellowish, right? So if you're looking at grapefruits, then you have to think, wait a second, I'm looking for a banana. Bananas are curved, not circular. So there can be differences in how you try to imagine the propositional code and what you think is the most important aspect of the propositional code. Now, as you can imagine, mental rotation does support kind of this idea of the analog coding perspective, because you just imagine a shape and you kind of rotate it in your mind. Whereas if you had to remember the description of a complex shape, kind of like these shapes, how would you describe, what would your propositional code be for this thing? You'd have to describe it to somebody and be like, well, I don't know, it's a stack of 3 blocks, and then you turn a corner, and then it's another stack of 3 blocks, you turn a corner, it's a stack of 2 blocks, then you turn a corner, and it's a stack of 2 blocks. So I don't know, maybe that's how you describe it, but that can be difficult, because then it's like, and if I rotated that stack of blocks 90 degrees right, what would that look like? And does it look like this rotation of things? Or if I had to make it even harder, if I rotated it back into space, so if I had to do a propositional verbal description of this shape, and I said, now rotate that back away from you by 90 degrees, does it look like this other shape? Now, obviously, that's a lot harder to do by describing things, so the idea usually is that mental rotation is an analog coding perspective. And similarly, by the way, doing mental rotation with a propositional code would take longer based on different scenarios, the same as it would analog. So it's not that they behave differently, it's that one is better than the other for sure. Another bit of imagery debate is, and I'll focus mostly on prosopagnosia, which is the inability to recognize human faces, in that there are some people that have a difficult time recognizing a face, and it's because they have a hard time creating visual imagery for faces. And that's usually the case is that people are more likely to be able to recognize something if they can keep a mental image of it. If they can't keep a mental image of it, then they have a hard time making a connection between the thing and some other mechanism of memory, like a semantic memory, something like that. So if you're unable to maintain the visual image for a face, for example, you have a hard time recognizing differences between faces, because you don't have a basis for a comparison for the face that you're looking at. more about the imagery debate, and comes from the Koslin research, is that 70 to 90% of the same regions that are activated during visual perception are active during visual imagery. So there is a used part of the brain that suggests that, boy, when you're trying to think of something, you're activating a visual cortex, and it's no different than perceiving something. So there's something about the perception that we have even of our mental images. So it's not just I have a perception of a stimulus out in the world. I actually have a perception of the thing that I'm trying to imagine, which is kind of cool to think about. It's kind of one of those like almost philosophical things. Let's see. Sorry, I just want to skip down just a little bit because some of this stuff is pretty consistent with what we've already been saying. Okay, let's skip down here. We're going to skip down a few slides to visual imagery and ambiguous figures. So when you have a mental image of an ambiguous figure, like in 7.2, which, by the way, is along the same lines as this image that I've just automatically popped in there, is the duck-rabbit illusion. And sometimes what we have a difficult time doing is distinguishing between ambiguous stimuli. So if you look at this, you kind of see like this little quasi-duck bill thing, but it kind of looks like also a rabbit lying on its back, which, by the way, is the problem that we have with ambiguous figures, is that you can't just say this is a rabbit duck kind of weird thing, right? You can't just say that. You have to describe it propositionally in terms of like what makes it distinct from some other thing, because there's ambiguity here. And by the way, if I were just to rotate this, you can kind of see how there's also some reflective ambiguity there. You know, you see the duck on top. Now it's actually underneath, but the duck is designed to not be ambiguous, but the rabbit is. And once you see one or the other, it's hard to see the opposite, which we call multi-stability. But you can create an analog code for this by like imagining what that looks like. But if you had a hard time with the ambiguous imagination part of it, then you would have to think about propositional ways to describe it using words. Another kind of example of how we use propositional versus analog codes is in this figure. So if you look at this figure, it's a six-pointed star. You might think of it as, it's two triangles overlap if you were going to use a propositional code for it. Very seldom would you think, it's a propositional code. I can describe it as this regular hexagon with regular equilateral triangles on the outsides of it, or whatever. You could describe that. And one of the tasks that came from this was to decide, so if you look at this object for a second, 3, 2, 1, and you decide something about it. So was a part of this pattern a parallelogram? And you would think, well, was it a parallelogram? I didn't see a parallelogram. But could it have been in there? If somebody used an analog code, they're not very likely to be able to recognize a parallelogram. But if people use propositional codes, they're a little bit more likely to have seen that. So if I go back and you say, well, wait, where's the parallelogram? Well, I can kind of trace it out a little bit. I'll start down here and go up and to the right and down back to the left and over. So there is a parallelogram within that shape, but you don't see it because there are different ways that you will propositionally code that information, because if you're going to use a propositional code, you'll see triangles and things like that. You don't really focus on this parallelogram that's in there. And if you use analog coding, you almost certainly don't see the parallelogram because you're just looking at the object as a whole. And within this is not a parallelogram, especially because if we are going to look at something from an analog perspective and we are going to look at it as distinct parts, what we're going to probably look at it as things in terms of their simplest explanation, which is overlapping triangles. Probably the easiest way for you to draw this. And second easily would be to look at the component parts, which is made up of these 6 equilateral triangles and a regular hexagon. So it can be very difficult with ambiguous figures, and this is an ambiguous figure because it could be considered multiple different things, although it's not as ambiguous as the duck rabbit from what we saw in the prior slide. Now, the classical description of the duck-rabbit illusion, by the way, is this one, where if you look at this and then you're asked to draw it from memory, if you just simply looked at it as an analog picture, you can probably draw it, but if you looked at it as a propositional code, it becomes a little bit more difficult, because if the propositionally, you would say, well, this is a hybrid duck-rabbit kind of thing with the duck ears pointing back, which are also the duck's bill. So you kind of have to describe it in ambiguous terms, and that can make it more difficult to create an image from, but just thinking of the image is a little bit easier to do. More research on the propositional code says that if you do have a strong verbal propositional code, it can dominate analog codes, because we know that analog codes are susceptible to deterioration over time. And if we're not able to keep track of our analog code over time, then it fizzles out. But if we have a strong propositional code, a verbal description, it's easier to recall, especially in an ambiguous situation, where if I have an ambiguous situation and I mix it up analog, that means that I don't really have a way to confirm my error. But if I have a strong propositional code that's based on rules and descriptions, I'm not likely to mix up the rules and descriptions so much. Koslin's research suggested that the distance that is between images and a mental image will increase the time to scan between them. So one of the examples of this is that if you imagine walking from your house to, I don't know, somewhere near to you, let's say it's a couple blocks away. Say you live in the city, you live in a house, and you want to walk to the gas station to get an icy, because that's what we get at gas stations, I guess. You can imagine just walking out your front door and turning a couple blocks and then going down to the gas station, and there you are. It doesn't take very long to imagine that. Now imagine walking somewhere that's 10 or 15 miles away, maybe to a different city. So if you close your eyes and you imagine doing that, it's going to take you a lot longer to do it. It might not feel like a long time in your imagination, but it's a lot longer than walking to the store. And that's because we actually take the path mentally in order to get somewhere. And we might skip things, but if I asked you to imagine every turn, that could be a lot more difficult to do, because you have to think about every little step along the way, even though something may be stored in an analog format. The same kind of research was demonstrated by looking at the hands on a clock. Being able to determine the difference between angles increases the response time increases as you have to make decisions in small differences. So this image indicates that there are two groups of people. There are people that have low imagery and people who have high imagery in terms of determining the difference between two angles of times on a clock. So imagine, and these are the examples from the text, so you can compare them to those. But imagine somebody says to you, compare the angle on the clock when the time is at 3:20 compared to when it's 7:25. And then determine which of those angles is smaller, so which has a more acute angle. When there is a small difference between the two times on the analog clock, then the people who have low imagery respond slower than the people who have high imagery. But that's the case in every angle. What's different is that is that your response time gets faster as the angle between the two times gets bigger, meaning that you're faster at making mental image decisions based on the difference between the mental images themselves. That's really not surprising, but it does support the effect that we tend to do better at identifying things when they are distinctions as opposed to when they are similar. The text from here covers a couple conclusions about visual imagery and discusses a little bit of differences between genders and visual spatial imagery. Just in brief, if I'm going to say anything about the gender differences, is that the only time that there's a strong effect or even moderate effect for gender differences on spatial ability, in visual imagery, it tends to be on spatial ability. Other than that, everything is pretty small. And even though there is a moderate effect size for some of the studies and a large effect size for one of the studies, the way that they tended to measure these things were kind of limited in ecological validity. So, for example, they would indicate that there were gender differences when participants had to judge whether or not a lighted stick was perpendicular to the ground in an unlighted room. So in those ways, they're not very meaningful because they lack ecological validity, and there's not really a big so what about it. So that's kind of all I want to get into for the gender comparisons, because everything else tends to be relatively equal. So next time somebody says men have better spatial skills, you can say, yeah, in one kind of area that's not exactly as meaningful. And that's just based on research. There might be some ecological studies out there that say something different, but based on the controlled research that we have access to, there really isn't that significant of a difference. All right, we've talked about mental imagery. Let's focus on auditory imagery for a little bit. In a similar way to mental imagery or visual imagery, auditory imagery is a perception of a sound, but it's not actually present. So there's a mental representation of a sound, and we've all done it before. We know what things sound like, laughter, a song, car sounds, whatever. And one of the things that we consider is the importance of the auditory. In the same way that we have visual imagery, auditory imagery helps us to make comparisons, to remember the sounds of things, to be able to know if somebody sounds like somebody else. It can be important to know if I have a mental representation of a sound, like of my wife's voice. If I hear her voice and it sounds off, I could make a suggestion that maybe she's not feeling well or something like that. Also, another factor in auditory imagery is vividness, in that some things are more vivid than others. By a long shot, it just depends on what you're listening to, what the image is. Auditory images, pardon me. Got to be careful when I use those terms. What's cool about auditory image and pitch is that there is a difference in the way that sounds sound, which sounds obvious, but that's true. But what's interesting about it in terms of auditory imagery is that our brains, if I wanted you to imagine a sound like a cat purring, and then immediately think of the sound of a police siren, it would take you a little bit of time, because your brain has to shift from the pitch of a cat purring, that kind of sound, and a police siren, wee-oo, wee-oo. Your brain takes time to make that shift, because we know that auditory imagery also leverages language centers. And if we leverage language centers, then those processes have to be activated and they have to move. Much like co-articulation, when we're trying to make a sound, if there is a difference between two sounds, it takes a little bit longer than if the sounds are similar. So in the same way, our brains have to activate those parts in order to make it work fast. But if it doesn't work fast, it's usually because the pitch is different, not because our brains aren't functioning the right way. They're actually functioning exactly the right way. You just have to travel between two imagined tones. Another example of kind of the nature of sound is this idea called timbre, spelled timber, go figure. But it's timbre, and it's the quality of the sound. So if you have two voices, for example, that are producing the same sound. So if I'm saying a word like caterpillar, and you say a word and it sounds like caterpillar, the pitch is different, but also is the quality of the sound. There's something different about it. Maybe I have a raspier voice than you. Maybe your voice is more nasally than mine, but there's a difference. And even if two people say the same sound in the same pitch, it will sound different somehow. Okay. Unfortunately, I can't show you the Pratt example, because that would probably violate the copyright for YouTube, because it belongs to something else. Same thing as the YouTube video, but surely you can click in the PowerPoint and view the YouTube video. Again, I can't show it here. Also, it would take time that I don't need to. Interestingly, when people think about the timbre perception and timbre imagery, there's high correlation. So what that means is that people have a pretty accurate representation of the quality of the sound if they imagine it mentally compared to the actual stimulus. In the same way, people are often pretty accurate about picking out instruments based on the same sound. So if you imagine what a violin sounds like when it plays a note, and then an oboe plays the same note, you're able to compare those mental representations against the sound that you're hearing and to imagine which. All right, let's shift gears a little bit from auditory imagery to cognitive maps, which is visual in the way that it's represented, but it's not visual in like you see the thing out there in the world. It's not a distal image, it's something that you create in your mind. So cognitive map is that mental representation of geographic information. So if you think about how to get somewhere, you're trying to give somebody instructions, you might do one of those things where you kind of like close your eyes and focus and try to imagine where to go. It's because we have cognitive maps of what the world looks like, and it's based on our experience with it. So it does tend to be a top-down element. There are lots of ways that cognitive maps show up in our lives. So when you're trying to think of like geographic representations of, like your home, you have a city, a neighborhood, country, whatever it is, people looking for things in a car seat, right? Like little kids are like, oh, I dropped something, and they have to imagine what the car seat looks like to reach down and know where their hand is when they feel a certain thing. There's a lot of ecological validity in cognitive maps, meaning that we can apply these things to real world and everyday situations, not just kind of some of these experimental things as well. So lots of different ways that we can use cognitive maps for sure. One of the interesting demonstrations about cognitive maps is something that the book uses in demonstration 7.4 with Roscoe's Edwardson demonstration, and it kind of looks like this, where if you have this design and you try to remember the design and where the numbers go on it, you can close your eyes, or if I took that away, you could imagine that you're standing at position 3 facing position 4, and you point to position 1. Okay, now do the same thing about standing at position 1 facing position 2 and pointing to position 4. All right, so if you were to do that, you would see some interesting results. You'd see some interesting results for based on the orientation of the map you looked at. For example, where this is oriented with 1 on top and 3 at the bottom right. And when you are orienting yourself to this and you're imagining standing at position 4, you point to position 1, it's reasonably accurate. But if you had to rotate this map, let's say, by imagining you're standing at position 1 facing position 2, pointing to position 4, the way that you would point to it in your imagination would be different than what the angle was as if you were standing at 4 pointing to 1, even though it is the same angle. Okay? So the judgment that you would make about the map when you try to recall the cognitive map from the orientation that you learned it is more accurate. You would have pointed at an angle. People have a tendency to straighten out the angle, for example, if they're facing at 1, if they're standing at 1 facing 2, that's what you're imagining, they would imagine that 4 is a right angle over here, and they would point almost completely to the left, or at least not as angular as the 4 is. Whereas if they're standing at the 4 pointing to the 2, they would point very angularly because that's the orientation that they recognize that they learned the map in. All right. So we're more accurate when the recall or the use of the map is in the same orientation, and we do this like when we're driving in a car using GPS. We have GPS shift the map around the position that we're heading because that's easier to conceptualize from a cognitive map perspective than if we are looking at a dot moving along a map and we have to think, oh wait, I need to turn left. Wait, which way is left? And you almost feel yourself moving into that orientation, being like, okay, yes, this is left, even though it's the same direction no matter what orientation you're in. Like left is south, for example, on the map that you're looking at. You would tend to have an easier time if you're in that first-person perspective as opposed to watching a dot move around a map. Okay. The good news is that cognitive maps are generally accurate based on research. Usually, The errors that we have are based on our rational strategies that are based on the distortions of reality. So if we're just not sure how far something is, or we can't recall if we turn left to get somewhere, that's where the error is going to happen. So some of the strategies that can interfere, or the lack of strategy, or just a conceptualization of the strategy that can lead us to have inappropriate or erroneous representations of cognitive maps, are based on the number of intervening cities, for example, in a map. And this is kind of what we usually use when we talk about cognitive maps. It's a good analog to an actual like geographical map or a political map or something like that, where we're looking at some distribution of cities or space or something. It's a good analog because that's kind of what we're talking about with cognitive maps anyways, even though it's not really just about maps. It's about like finding something in a particular space, or using proprioception to reach for something that you can't see or something like that. But anyways, the mapping is distorted by the number of intervening cities. So knowing how far away something is, things feel further away the more cities there are between them. There's also category membership, which we'll look at in terms of what things belong together, and then also landmarks. So when we think about the distance estimates and the number of intervening cities on a map, the Thorndike example is pretty interesting because they're able to show maps and determine how far away things are according to people's recollection or reckoning, based on the number of stops, or what we call intervening cities, between 2 points. All right. So the example that they used in their research was that they showed people a map and then the people would study it until they could reproduce it. Okay, and then between any two given points, there are either 0, 1, 2, or 3 cities that are between the 2 points. And then they were asked to estimate the distance between particular cities. And what they found was that the number of intervening cities had a very clear-cut difference on the distance estimate. So this is kind of what it would look like. You would show somebody a map, and this is exactly from the original Thorndike experiment. I was able to find that through a little bit of digging. But this shows how many cities are between some particular points. And you have even a scale that, 25 miles is whatever this distance is, whatever, a quarter inch, I guess, or whatever it would be on the map. It's all to scale. And then maybe a full inch is 100 miles, and you had to determine how far away 2 cities are. And what they found was that as the number of intervening points went up, the estimated distance in miles went up. But what happened was that you also get more of a difference between the actual distance and the perceived distance. For example, in this first distance, there was only one intervening city between these 2 points, and they estimated that the distance, about 80 miles or so, but the actual distance difference is only 50 miles. Okay, and then as you go up, so as you add cities between different points, you have an increase in the actual overall distance error between the two estimates. So in this example up here, there is an example where there are 2 to 3 intervening cities. They estimated about 160, and they were 125 miles off altogether. So, that was the actual difference in the distance. So you can tell that there's roughly a 40-mile difference between those things, as opposed to only 25-mile difference or so, and when there's only one intervening city. So, when we think about like estimating how far things are away from each other, if we know that there are landmarks like cities between 2 points, we're likely to overestimate those things, as opposed to if there's just 1 or 0 intervening cities. Like, for example, between Utica and Lewis, you might estimate that maybe that's like 125 miles, and maybe that's correct. But the difference between, let's say, Butler and Meadow, you might estimate more because there are more cities between them. Something else that interferes with our ability to determine a sound cognitive map is category membership. There are a couple of interesting things that come along with this, but what happens is that the Hurdle and Maskelow study asked people to learn a map of a town and estimate the distances between the pairs of locations. And one of the things that they found was that there was an overestimate of distance when they were looking at two things that didn't belong together, like two different cities or two particular landmarks between two cities, than similarly distanced items within the same city. So if there was a landmark in two different cities that were, let's say, 50 miles away, and a landmark within a city, I guess that's a bad example, 50 miles is big for a city, but let's say there's a huge city and there's a landmark 50 miles away from each other. The people are likely to estimate that the two landmarks are farther apart if they're between two different cities than if they're within the same one. And here's kind of an example of what this might look like on an actual map. I was able to get a Google map and put down just kind of a little tracker on there. And what's interesting is that the very tippity top of Brazil and the very tippity bottom, is that it? I don't know. The very bottom of Brazil is 2,719 miles apart. So the longest distance you can go in a linear fashion in Brazil is 2,719 miles. What that means is that the top of Brazil to the bottom of Brazil is farther away than the top of Brazil is to Canada. Right? There's a little bitty south side of Nova Scotia, Canada, that is closer to the top of Brazil than the top point of Brazil is to the bottom of Brazil. And this is probably surprising to you, and it would be surprising because if I said to you, what's closer to the top of Brazil, the bottom of Brazil or Canada, you're likely to say, well, wait a second, it's got to be the bottom of Brazil, right? Yes, because when we create these cognitive maps or understanding of the world, we automatically assume that two things that are categorically related, like something within the same country, must be closer to each other than something that is not part of the same country. By the way, there are a lot of these other kind of anomalies that show up. There's some in America too, but this one's kind of the most stark, I think. Things like northern Texas is closer to like 13 other states than the bottom of Texas, something like that. Don't quote me on that one. That's something I'm just kind of remembering from looking at these things a while ago. The Mishra and Mishra example is interesting because they asked people if they were placed in a certain area where they would be equidistant between vacation homes. They would ask, would you rather have a vacation home in Washington or Oregon? And they would make a decision. The control group made a decision based on just not knowing any information. They were just asked a question and they chose. But one group was told that there was an earthquake in Oregon, which is in a city the same distance away from where they were setting up this scenario. So it was 200 miles away in Oregon. And then another group was told the same thing, but that the earthquake was in Washington. What they found was that in general, people would gravitate toward decisions that were on the same side of a particular border versus something that was on the opposite side. Even if the difference between them, for example, where the earthquake happened, was exactly the same between them. And this chart summarizes that. You can also refer to the text to get a little bit more of an in-depth understanding of this. Or if you're really excited, you can go find the original study. Okay. The landmark effect is kind of like along the same lines as the border bias, in that we tend to provide these estimates based on some kind of group categorization, a little bit from group categorization, but also based on the number of, or whether or not you're traveling to a landmark or not. And what this looks like is that if I am estimating how far a particular distance is away, but I'm just traveling between two things, I'm going to a gas station, whatever, and the gas station is 10 miles away. I'm going to go to a gas station, no problem. I can probably estimate that it's 10 miles away. Imagine you're going to a historic monument. Because you're going to a place that's more of a landmark than just a gas station or whatever, you're likely to indicate that is shorter than what it actually is. So if it were 10 miles away, you might estimate it's only 8 miles away or whatever. Something else that happens along those same lines is that somebody might say, come to my house instead of me going to your house because my house is closer. It's like, well, wait a second. If you're coming from your house to my house, we're the same distance, but we kind of assume this landmark status about certain things, and you might say that see your house as quote unquote the landmark. It's not an actual landmark, but our brains kind of think of it as come to my house. It's closer, but even though it's the same distance either way. Another example of the way that we use cognitive maps is that we tend to take ideas that are irregular or geographical representations that aren't necessarily completely linear or that are curved or whatever. We tend to straighten those things out. And again, this kind of harkens back to an idea about how we save information schematically, and we tend to make things a little bit more angular or regimented than they actually are. So if you're trying to estimate like degrees and angles and things like that, you might think to yourself, turn right here, but the right turn might be a 45-degree turn, which is still a right turn, but we don't say, hey, make that kind of like gradual veer. You just say turn right. Because schematically it's easier to think of it that way. And even though you're driving, it is technically quote unquote a right turn. In our minds, we'll still establish that as more of a right angle than it actually is. Another example of using cognitive maps is the relative position effect. If I asked you what country is south of Michigan, you'd be like, well, wait a second, are you talking about Mexico or Cuba? I was like, no, the country south of Michigan, as you can see, is Canada. So Canada is south of Michigan in a couple ways. It's directly south of downtown Detroit. Granted, that's a small portion of Canada, but it is Canada nonetheless. We use these heuristics to talk about, these positions, which is why it's typically easier to remember the Midwest states and what they're called than the states that are in New England, because the states in New England don't kind of like nest and have these like little angular connections, and it's more difficult for us to conceptualize them than the ones that are in the Midwest. So if something geographically is slightly tilted, we'll straighten it out. So for example, if you thought that, Canada was north of United States, but you forgot about the fact that Ontario comes down into Detroit, for example, it's because you probably thought that, just heuristically, that Canada is north of America, which is true most of the time, but not in some cases. And we also remember that things geographically are more lined up or straighter than they actually are, which is the alignment heuristic. The rotation heuristic is also in play here, in that we tend to rotate things and make them more vertical than they actually are. The example from the book talks about which city, San Diego or Reno, is further to the west. And you might think, well, obviously it's San Diego, it's in California, but the answer is Reno. It's actually further to the west than San Diego. And that's because we tend to take things and make them more linear than they are. Or if, another example, and you can kind of look at this, maybe I can show this on this, is that, is South America, is it directly south of North America? Like, yeah, probably. But the reality is that most of South America is east of Michigan. So if you went straight south from Michigan, you might never hit, depending on where you are. If we're in Olivet, you might never actually hit South America. Just a very interesting kind of phenomenon with that as well. Again, this kind of expands on a little bit on the rotation heuristic. You can feel free to read through those as you'd like. The alignment heuristic, again, what we just mentioned, kind of talks about how we tend to make things straighter and more linear than they actually are. We typically think of America being on the same latitude as Europe, and pardon the drawing, this is from the text, it's not the best drawing in the world, but America, by and large, is south of Europe. And what's interesting too is that Philadelphia and Rome are on the same latitude. So most people think that Rome is further south than Philadelphia, when in fact Philadelphia is further south, or New York or whatever. You tend to think of Rome as being kind of a southern destination, and it just isn't. Okay, so I'm just kind of scrolling through. I think, let's talk about one more thing. I want to talk about situated cognition, then I think we'll be done with this one. So I'm going to skip down just a little bit. to situated cognition, and I think this has popped up at least informally in some of our lectures. But when people learn information or they think of a map or whatever, they use their immediate environment in order to conceptualize the information. So there's if you aren't in the in-person class, then you've seen this from an earlier chapter. But using the visual spatial sketchpad, there was a demonstration where you would do something like listening to instruction and imagining where you're going. So it'd be like, get out of your house, walk out the front door, turn left, walk 2 blocks, turn right, whatever. And then I say, now where are you now? Or what are you facing? Or what did you walk by? So you would have this kind of idea of what you walked by and what direction you were facing. You can do that with a lot of expertise. But one of the things that you might not be thinking about is the situated cognition approach is when you develop that cognitive map, what was the weather like? Is it the weather that it currently is? Did you imagine you walked out and it was, snowing or whatever? Did you, and maybe it's in the middle of summer, or did you walk out and think, maybe it's a certain day, or you maybe even smelled some things, which is a little bit different than what we're talking about, but you realize that you incorporate less of other information. And what that means is that the way that you conceptualize your cognitive map is also based on some kind of situated cognitive approach that you used when you develop that map. Lots of times people will just recruit what's going on outside. You might just think, okay, it's cloudy outside. So when you have this cognitive map and you know it's cloudy outside, you're probably likely to use that cloudiness as your situated cognition. What's funny about it is that when I developed some of these demonstrations, like the one I just mentioned to you, it was a certain weather outside. So when I recall the demonstrations, I immediately think of the weather as it was when I did it, even though I might be doing the demonstration in a cold fall semester. When I did it, it may have been over the summer, and I'm imagining walking outside of a building, and it's summertime, even though there could be 3 inches of snow on the ground or whatever. So we use information about our environment to reinforce our learning, which is important because if we are learning in a particular situated cognition or a certain environment, then recalling that information in that same environment is also very helpful to do. That enhances our learning, it enhances retrieval. So there's a good tip if you're taking a test or whatever, try to study in the same environment where you'll be taking the information out. That way it can be more helpful to rehearse that information and bring it back. We've also talked about that in terms of like memory palaces and things like that as well, or the method of loci, which is what that's also called. Okay. Oh boy. We even skipped some of this stuff, and that was quite a chapter. So it's a cool chapter though. Mental imagery and cognitive maps is pretty fun stuff. So that's it for that. Reach out if you have any questions. If something wasn't clear, or you need some additional information on something, I'm happy to help. Or if I misspoke and you're like, hey, that doesn't sound right, let me know that too. We say lots of words and some of them are kind of technical, so help me out when you can. Otherwise, I look forward to seeing what you can do with this information in the modules.